Okay, I'm finally here. I had to reboot my computer twice. I don't know what was going on this morning. Um, it showed in the task list or whatever they call it, the open programs that Zoom was running, but it was not responding, and I don't know what was happening. Anyway, today we're going to be looking at the relativistic Doppler effect, and I'll just switch over to the visualizer. I don't know what kind of focus it's in. That looks pretty good. Get rid of all this other junk. It's focused. That. Okay. This is not the Doppler effect. We had a Doppler effect for sound back winter quarter. And with that, it was heavily dependent on the fact that the sound traveled through a medium only at a particular speed. And it's actually possible for an object to be traveling faster than the speed of sound in that medium, which we didn't work that into the Doppler effect, but we could have had things like that happening. But in the case of light, there is a relativistic Doppler effect, and let's see, I think I'll put it on scratch. Well, I'll just go ahead and write it here. The frequency shift for the relativistic shift ends up being C plus U divided by C minus U times F naught. And this would be the source approaching the observer, although it turns out it's all relative motion. So if the listener and the source are moving together with a relative speed of U, then this is what the frequency shift is going to be. Now, if you just take the F is equal to C over lambda, you can switch this expression around and you'll get the one for the wavelength shift. And the wavelength shift ends up being C minus U over C plus U times lambda naught. So you could play with just replace F with C over lambda, and then you'll have a fraction on both sides. And if you flip both of them, you'll get to this thing. And this is for the source approaching the observer. In this case, you'd have a smaller numerator than denominator, and so the wavelengths would be shifted towards shorter wavelengths. And U is the magnitude of the speed, by the way. So that would be the effect that you get. And in astronomy, when a source is, both of these are source toward observer, although again, it's just relative velocity that matters. In astronomy, you hear the terms blue shift and red shift, which unfortunately many people tend to think, okay, it's going to look blue, or okay, it's going to look red. And that's not the case at all. Usually the shifts are so subtle that nobody'd notice it. For instance, between stars in the Milky Way galaxy, if there's some wavelength that has, maybe in a laboratory, and I'm just going to make one up here, 638.751 nanometers might be the wavelength of it. Between stars in the Milky Way galaxy, a typical blue shift might be, the observed wavelength might be something like 638.715 nanometers. Okay, you cannot detect this with your eye at all. You'd swear both these colors are exactly the same thing. And so, and a red shift is if it's moving away. So if you end up just taking the reciprocal of this thing, if it's moving away from you, and similarly with that. But that's a typical thing. Now with galaxies, they can be shifted more, but they're still not something that you could trust the eye to. And plus, blue shift and red shift can happen for light that's outside of the visual spectrum. And so, for instance, you could have an ultraviolet wavelength get blue shifted, and it's best to just think of this as meaning shifted to shorter wavelengths. So I wish they had just stuck with that. And I'll just say shifted to shorter lambda, shifted to longer lambda for the red shift. We probably won't use those terms blue shift and red shift, but you do hear them a lot. The reason for that is that if you're confining yourself to the visible spectrum, and the visible spectrum lambda equals 700 nanometers out here on this end and about 400 nanometers on this end. And if you took something that was right in the middle, say at 550 nanometers, okay, if the source of light is moving away from you, that spectral line might shift toward the red end of the spectrum. And why they called it blue shift instead of violet shift, I'm not sure. If that the source that's producing that light is moving toward you, the light would be shifted toward the violet end of the spectrum. That's what they call blue shift. So it's just kind of a weird thing. But again, most of the time the shifts, at least for local, and by local I mean within the Milky Way galaxy, that kind of objects, the shifts are so subtle that they're not detectable with the eye. But they still have that name red shift and blue shift. And if you would just think red shift shifted to longer wavelengths, blue shift shorter wavelengths, you'll be better off. So those are what the formulas look like. And this is the source moving toward the observer. If the source is moving away from the observer, or better to think that the observer and the source are moving apart, you just flip both of these fractions. And so the frequency goes to lower frequencies because you'll have the minus term on top and the plus term on the bottom. The wavelengths go toward longer wavelengths, and try to reason that out so you get a good understanding of it. And that should be okay there. One of the things that we can do is look at this wavelength shift formula in the case of speeds that are much less than the speed of light, which is typical for stars in the Milky Way galaxy. And let's look at what happens in that case. I'll just get some scratch paper here, and I think I'll fold this one in half. So here's a question. What if U is much less than, and that's what I mean when I have two less than signs, C, okay? And in this case, what's often done is that we look at the shift in wavelength divided by lambda naught. By the way, lambda naught is the wavelength you would observe if you were to observe a particular spectral line in a laboratory or some source of light that's at rest with respect to you. And the delta lambda would equal the observed wavelength minus the laboratory wavelength divided by that laboratory wavelength. Well, this is going to simplify if we plug into this formula here. we'll have, well, not really simplify it first, but we'll fix it. C minus U over C plus U times lambda naught minus lambda naught divided by lambda naught. We've got lambda naughts all over the place, and they divide out, and we'll just get the square root of C minus U over C plus U minus 1 is what shows up there. Well, I'm going to take the top and the bottom of this fraction in here and multiply by 1 over C. And when I do that, this becomes the square root of 1 minus U over C divided by 1 plus U over C minus 1. And remember, U is much less than C. Does anyone sense a series expansion coming on? Okay, there may be a series expansion for a fraction. I'm not sure, but what I'm going to change this into is 1 minus U over C to the 1/2 times 1 plus U over C to the minus 1/2 minus 1. And so, and now we can do our series expansion, our famous series expansion, which is 1 plus x to the n. I've almost got this thing memorized now, is equal to 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus dot, dot, dot. But we never even use this term, so we'll just stick with the first two terms. And for this thing, my n is going to be 1/2. My x is going to be minus U over C. And so this whole thing will end up becoming, and this is delta lambda over lambda that we're calculating so far. Let's see, where was I? 1 minus U over 2C. So that's the first one. The second one also becomes 1 minus U over 2C. So I'm multiplying those two things together, and I'm still subtracting 1, and supposedly this still equals delta lambda over lambda. Well, I can multiply those two things together. These are just binomials, and I would get 1. I'm foiling this here, so I'd get a minus U over...
Positive?
Pardon?
Shouldn't one of them be positive? Because you have 1 minus U over C and 1 plus U over C.
Let's see. Except one of them has an exponent of 1/2 and one has an exponent of minus 1/2.
Oh, but never mind.
Okay, yeah, sorry, I just raced by that. I didn't even mention it. Yeah, otherwise it would be. But let's see. Oh, the F, that's the 1. The O is the minus U over 2C. And the inside is another minus U over 2C. And let's see, and then I'll have plus U squared over 4C squared. Well, if U is much less than C, U squared over 4C squared is going to be negligible. And so I'm just going to kind of drop that one off the mark and not count it. And what I get is, when I add these two together, I just get minus U over C is equal to delta lambda over lambda. Now, this is the case when the two objects are moving together towards shorter wavelengths. If we'd done it for the two objects moving apart, I would have had plus signs on both of these things, and I would have gotten a plus U over C. But in general, if you have speeds are slow, and this works just fine for the relative speed of stars in the Milky Way galaxy, or would unless you get close to the center of the massive black hole in the center of the galaxy, where there's stuff orbiting that are going at like 40% the speed of light and things like that. But that's not the case for most of the galaxy. Anyway, this delta lambda over lambda is just equal to the relative speed of the things divided by the speed of light. And if they happen to be moving toward you, you put a minus sign on it. If they're moving apart, you put a plus sign. Or you recognize if they're moving toward you, you're going to see shorter wavelengths. And if they're moving away from you, you're going to see longer wavelengths. So, but that's a nice little approximation. And this is the one that when I teach in the astronomy class, we would start with this and not go anywhere near that stuff up here. But that's almost more mathy than people in that class can handle sometimes. Alas, even though they have completed our Math 90, whatever it is, algebra course, apparently it's possible to complete an algebra class and not have anything stick on the way through the brain. All right, well, let's try some sample problems wherever I put them. Here they are. Spectroscopic measurements of light at lambda equals 397 nanometers coming from a galaxy in Ursa Major reveal a redshift of 20 nanometers. That's actually pretty large. Usually it's out past the decimal point on the nanometers. What is the recessional speed of the galaxy? Well, let's see. I don't know if that's small enough where we can use the approximation formula. So I would probably use the full-blown formula in this case, where now redshift, that means shifted toward longer wavelengths. And this would be, so instead of 397, it would be 417 nanometers. And that's going to equal the square root of, if it's moving, or if it's a redshift, it's moving away, I'll have to swap the signs on this. So it'll be C plus U over C minus U times the 397 nanometers. And I'd almost rather use the other thing here. I think I'm going to convert this to beta. So I'll multiply 1 over C times both of these things. And when you distribute that through, this will become, let's see, the square root of 1 plus beta over 1 minus beta. And I'm going to call this lambda naught and this thing lambda. And then at the end, I'll plug in the numbers because I just don't like writing them that much. Okay, well, you can probably guess what we're going to have to do, and that's to solve for beta. And we'll see if it's, maybe when we're done, once we have beta, we could try the approximation and see how well it works. And that's the lambda over, or lambda naught over lambda equals V over C. But in this case, 20 out of 400, that's a fairly significant shift. So let's see, square both sides. I would get 1 plus beta over 1 minus beta. And I'd have that times lambda naught equals lambda. I think I'll just solve for the, I'll just multiply out from underneath by that. 1 plus beta times lambda is going to equal 1 minus, whoops, lambda naught is going to equal 1 minus beta times lambda. And let's see, lambda naught plus beta lambda naught equals lambda minus beta lambda. Lambda minus lambda naught is going to equal beta lambda naught plus beta lambda. Yeah, I swapped sides. Swapped both sides. That's all right, which is beta times lambda naught plus lambda. And beta, more scratch paper needed. Beta will equal lambda minus lambda naught divided by lambda naught plus lambda. So lambda minus lambda naught is going to be 20.
Did you square it somewhere?
Oops,
Yeah,
I did.
early
Let's
on,
see. So these
we
should have
needed
been
to square both
squared,
sides.
right? Yes, I did, but I didn't square those. Okay.
Yeah.
So everywhere we've got those things, they need to be squared. Yeah, talking and writing. Let's see. Okay, that'll make the math considerably different. Anyway, let's see. Yeah, there's nothing I can do about it. I'm just going to have to square them, I guess. So beta is going to equal lambda squared minus lambda naught squared over lambda squared plus lambda naught squared. Okay. Calculator time. And I have to remember lambda is 417 nanometers. Lambda naught is 397 nanometers, which is, well, it's probably outside my visual spectrum, but maybe not for everybody. Anyway, did I have that in the right order? I don't remember. I guess I did. Yeah, this will actually be, oh, redshift. Yeah, this will be longer than that. Okay. So, wrap everything in parentheses. And I'd get beta is about 0.049. And that might be about as many significant figures as we can do. That's about 5% of the speed of light. So that would be the recessional speed. Remember, this is V over, or U over C that we're using here. So that's, I don't know, it's fast, but let's see how we would do with the V over C thing. If we had the delta lambda over lambda, that's just 20 nanometers divided by the delta lambda over lambda naught, I mean, over 397 nanometers. And that's pretty close, actually. Yeah, this is about 0.050. So not that significant a difference between the two, but if we're only talking 2 sig figs, there is a slight difference, but still not too bad. We almost could have gotten away with the approximation and wouldn't have been far off in this case. Although these things start stacking up the faster you're going. So if you were going instead of 5% the speed of light, 10% of the speed of light, you'd probably have a larger error. So, okay. may hang on to that. A distant galaxy is moving away from us at a speed of 2 × 10⁷ meters per second. Calculate the fractional redshift in the light from this galaxy. Well, and they use lambda prime. That may be what your textbook uses. This is going to be, let's see, 3 × 10⁷ would be 10% of the speed of light. So this would be about 66 or 6.7% of the speed of light. So it's a little bit faster than the one that we had before. So we can see what the fractional redshift is in this case anyway. It's moving away from us again, so we would use lambda. I'll put a prime on it like they do. It's going to equal the square root of c plus u over c minus u times lambda naught. And actually, we could maybe use the approximation, but let's try not to, I guess. So lambda prime minus lambda naught over lambda naught ends up being the square root of c plus u over c minus u minus 1 when we get done with it. So let's see how much of a difference this makes. And this is, yeah, delta lambda over lambda. So let's just go ahead and calculate that and see if it comes out to how close this comes to v over c when we calculate this. So the square root of c, whoops, have to put in numbers now, 3.00 times 10⁸ meters per second plus 2 times 10⁷ meters per second. That's going to turn this into 3.2 times 10⁸. And then on the bottom, we'll have the 3.00 times 10⁸ meters per second minus 2 times 10⁷ meters per second. So that'll change this into 2.8, and everything divides out except 3.2 over 2.8. So we'll see how significant this is. Second square root of I get about 1 point, we've only got 2 sig figs, so about 1.1 for delta lambda over lambda. Now, how does that, or how close is that to v over c? Whoops, I've got a -1 here somewhere. So it'd be 0.1 is what it ends up being. Yeah, I lost that. Okay, so just v over c in this case, or u over c, would be the 2 times 10⁷ meters per second over 3 times 10⁸ meters per second. That one is exact. Oh, I can actually call this well, I'm pushing things a little bit. 0.07 about, and this would end up being about that too. So yeah, I would get about 0.07 for this thing as well. So pretty close. Even down here at, well, it's less than 10% of the speed of light. I'd probably say 10% the speed of light is where you'd want to maybe use as a cutoff, or right there you'd want to calculate it both ways and see which one is better. Okay, let's see. We had a relative velocity problem that had a galaxy going away from us at 0.87 c. And for that galaxy, what would be the observed wavelengths for the spectral lines in hydrogen with wavelengths of 410 nanometers and 656? Now, in this case, we're actually after the observed wavelength itself, not the fractional shift. And it's moving away, so we'll be using the C plus U over C minus U times lambda naught. And we may as well just calculate this term and then multiply them by those two wavelengths there. So the square root of C plus 0.87 C, and then divided by C minus 0.87 C is going to end up being 1.87 divided by 0.13 down here. So that'll be a significant difference anyway. And 3.79. Okay, this is the case with, I think we were talking about quasars the other day or not. I can't remember for sure. Was that in this class? They were the things that were discovered in the 1960s where they saw these light emitting objects and they observed spectral lines in them, but they were shifted so far that they didn't recognize them. So if we take that number and multiply it by that, the lambda that's observed is going to be 410 nanometers times 3.79. And I think I'll store that in X. Okay, so that thing times 410 is going to be 15, I'll call it 1560 nanometers. And then for that red spectral line, by the way, both of these, yeah, that does mention there for hydrogen, times the same number. And this one ends up being 240, 2490 about nanometers. Okay, this is way down at the violet end of the visible spectrum, and it's going to be shifted so far that it's in the infrared. And that one that's out on the red end of the visible spectrum is even farther into the infrared. So these are shifted completely out of the visible spectrum. And these are the ones that when these things were discovered, the shifts were so much that they didn't see any recognizable patterns in the visible part of the spectrum. And the reason for that is the visible part of the spectrum that you're seeing from this was stuff that was way down in the ultraviolet part of the spectrum getting multiplied, and that shifts it into the visible part. And so for a while, these were quasars, which is short for quasi-stellar objects. And that's what they were reported as anyway. So then somebody started looking a bit farther outside the visible spectrum and realized what it was that they were seeing. But that's pretty amazing to have stuff shifted by that much. Let's see. This formula, you would go through pretty much the same thing we did for the wavelength formula. You might try that on your own, and we would get the well, wherever we did it, I don't know what piece of paper I was using. Not that one. Don't know where it went. Anyway, that development we did with the series expansion on the earlier part, you'd just start with with this expression and expand the top and the bottom here like we did, and you get a change in frequency divided by the initial frequency. And they don't, I guess they'd probably call it f prime minus f divided by f for the fractional shift in the thing. And so you'd get an expression very much, but it ends up being plus or minus v over c, depending on if it's moving away from you or not. So here's a chance to try that out for something a little more mundane. A radar transmitter bounces a signal off an aircraft and observes a fractional increase in the frequency, delta f over f, of 8 times 10 to the minus 7th. What's the speed of the aircraft? Well, this fractional shift in the thing is just what we stick in there for delta f over f. So 8 times 10 to the minus 7th. Oh, that is it. That's the delta f over f. And so that's going to equal the speed divided by the speed of light. Radar signals travel at the speed of light also. So that's something that happens. So the speed is going to be 8 times 10 to the minus 7th times 3 times 10 to the 8th meters per second. And that looks like 24. 8 times 3, 10 to the 8th times 10 to the minus 7th is times 10 meters per second, which is 240 meters per second. And that's pushing things a little bit with the sig figs, but that's about what it is. Let's see, it should be 6 times 40, 6 times 90. This would be about 540 miles per hour. So that could be a commercial airliner, actually. They can go roughly that fast. So, okay. There's another kind of Doppler shift that occurs. And if I could, it's one that happens, that does not happen with sound. And it's the transverse Doppler effect. Which is kind of crazy. And it's purely due to time dilation. And for frequency, it shows up this way. It would be f naught divided by gamma, and then you've got a 1 plus u cosine of theta divided by c. And this is going to need some definition here. If here's the observer over here, and here's the moving object, and let's suppose that the velocity vector u is in this direction, then this would be theta here. It's the angle between the velocity of the emitter. Whoops. Yeah, that's the emitter. And the line of sight to the observer. So if it happens to be perpendicular, if u happens to be perpendicular to this r vector here, we could call that just an r vector or something. But anyway, if it happens to be perpendicular, then the cosine of 90 degrees is 0, and you just have the fundamental frequency divided by gamma, and purely due to time dilation. But if you have this other thing going on, then it's a mixture of the two, a mixture of radial velocity, the fact that this thing is partly coming toward here, and transverse velocity. And this is something that a lot of observations are done of, the Gaia spacecraft was put up by the European Space Agency. And in addition to measuring star positions very precisely, they're also determining their velocities, both radial and transverse. And so it's trying to produce a three-dimensional graph of as many stars as possible in the Milky Way, of not only their current positions, but also the directions they're moving. And so we can look at how the Milky Way is going to be changing in the future. And it's just working on stars within the Milky Way. Anything else is too far away and too hard to determine those things for. But it's kind of a neat thing. So let's figure out a problem for that. We're going to put ourselves in a strange place for this one. This is one that just occurred to me as I was looking at this stuff this morning. Put yourself at a location near, but not too near, and we'll stop after this one because we're already running late. Supermassive black hole in the center of our galaxy. A star is moving tangentially, or let's see, I'll say perpendicular to, and I'm going to abbreviate, perpendicular to your line of sight, L-I-N-E of sight, at 0.33 C, and there actually are stars moving that fast in the vicinity of this supermassive black hole. What will be the observed frequency of the, let's see, okay, we'll just pick the 656 nanometer line in hydrogen. Now, this thing is in terms of frequency. It's not in terms of wavelengths. So we'll have to figure out the wavelength or the frequency of this, but that's not hard. The frequency is going to be 356. Whoops, nope. How about 3.00 times 10 to the 8th meters per second, C divided by lambda, and 656 times 10 to the minus 9th meters. And so we'll get hertz or per seconds here. And we can figure out what the shift is going to be in this case. And this will be purely due to, because it's moving perpendicular to your line of sight, not toward you, it'll be just the F over F naught over gamma thing in this case. So the frequency, whoops, clear that. 3 times 10 to the 8th divided by 656. And it's a reasonably high frequency, 4.57 times 10 to the 14th hertz. This is why we usually talk about light in wavelengths of nanometers here. It's just more convenient than dealing with these things. So that would be F naught. So 4.57 times 10 to the 14th hertz, but it's going at 0.33 times the speed of light. So gamma is going to be 1 divided by the square root of 1 minus 0.33. Whoops, that's not a point. 0.33 squared. And it's not all that much. 1.06 is about what we get out of this. So that 4.57 times 10 to the 14th and I'd get about 4.31 times 10 to the 14th hertz. So not a huge shift due to this purely transverse stuff. So, but that's the way it works. You'd actually have a much more significant shift in the wavelength. Well, if it was moving at that speed toward or away from us, you'd have a more significant change in the frequency, I think, where the gamma is not showing up in there. In fact, let's see, if it was moving toward us at that, what would it be? We'd have 1.33 divided by 0.67. Yeah, if it was moving purely along a line of sight, you'd have a 1.4 that you'd be multiplying the frequency by instead of dividing by 1.06. So, okay, we better stop there. And sorry I was late. I don't know what was going on this morning with Zoom. It just would not open. But it seems to have recovered. So, or I haven't heard from anybody in a while. Anyway, tomorrow I want to talk about actually the last lab. The electronics is not working the way I'd hoped it would. Don't have a way of powering those circuits for you. So that was my screw up at the beginning. I should have sent something with you, or also ordered a power supply for those kits, or not a power supply, but a transformer. However, what I'd like to do tomorrow, in addition to looking at general relativity, is look at the E over M lab, the charge to mass ratio of the electron, and some of the data, and just show you how that could be calculated. I have data from either 2 or 3 years ago. I saved the data that the students gathered, and we put it all together and averaged out the things with that. And we'll look at how, from the measurements we took, how we can figure out that charge to mass ratio of the electrons. So we'll do that tomorrow as well. And there won't be anything to turn in on that, but I would like to talk about it at least. So that's what we'll do tomorrow. And then next week, Monday and Tuesday, we'll have review for the final. We'll just look at stuff we've done all quarter. And the final is cumulative, but only over this quarter's material. So I think in chemistry, don't they do a cumulative over the whole year thing?
Yeah.
We're not going to do that. So yeah, I don't know if when I took chemistry, if we did something like that at the end of the year or not. Probably not. All righty. Well, I'll see you then. And hopefully things will work better tomorrow. I'll check much earlier. I tried logging into Zoom at 10 after 9 this morning and it failed. I eventually rebooted my computer and it failed again, and then I rebooted it again and it worked for some reason. So I don't know what was going on. But see you tomorrow.